Dr. George Matzko is a research chemist and professor, and he has agreed to join us to talk about what we have learned about solar eclipses. Throughout history, it has been during solar eclipses that we have learned so much about the sun and the stars, about starlight, and about the nature of the universe. Now let's join Dr. Matzko. Thanks again for joining us on this edition of the broadcast. We're talking to Dr. George Matzko. Dr. Matzko has a PhD in analytical chemistry from Clemson University. And on the previous broadcast, as we talked about that, we learned a little bit more about him. Dr. Matzko, we were talking about light in the last discussion, especially because we are considering what happens in solar eclipses and a little bit about what we've learned in solar eclipses historically. Let's talk again about light, and the visible light is part of a larger electromagnetic spectrum. So walk us through that, if you would, and help us to understand that.
Okay, when we think of light, we're thinking about the visible part of the electromagnetic spectrum. But we need to remember that that's just for human eyes, that sometimes animals can see parts of the spectrum that we can't see, for example. Like pit vipers, like rattlesnakes, can see in the infrared, and birds can see in the ultraviolet. And we can see a narrower range. You know, it's interesting. There's one animal that can see both in the infrared and the ultraviolet. And I often ask the kids to guess what it is, but it's the humble goldfish. The goldfish can see both in the infrared and the ultraviolet. I have no reason why God gave it that ability. But like other forms of electromagnetic radiation, light has both wavelength and frequency characteristics. So the wavelength determines the color of the light, while the frequency determines its energy. Light, like all electromagnetic radiation, travels at the speed of light in a vacuum, which is about 300,000 kilometers per second. Light, along with other electromagnetic waves, propagates as a transverse wave, which means we have electric and magnetic fields oscillating perpendicular to the direction of propagation. You know, it was interesting. We're going to talk about sound in a little bit, but back in the 19th century, scientists did not think of outer space as being empty. I guess they could have just read that verse in the Bible where it says he hung the earth upon nothing and believed what God had said. But anyway, they thought that the space was filled with something called the luminiferous ether. And because they're trying to solve the problem is how does light get from the sun to the earth? And all the waves they knew about, like sound waves or ocean waves or whatever, something was waving. But with light, it's a self-propagating waves. The electric field produces a magnetic field, which produces an electric field, which produces a magnetic field, and it can actually go through empty space and be propagated that way. So that's unusual. But all the different frequencies of electromagnetism can do the same thing. And light also has a quantum nature. We talked about that last time. It has a wave-like property and particle-like behavior. And that's a fundamental characteristic of all electromagnetic radiation. Now, what's the difference? Well, a light specifically refers to that portion of the electromagnetic spectrum that's visible to the human eye. That's about 400 to 700 nanometers. There are other forms of electromagnetic radiation, such as radio waves and microwaves and infrared, ultraviolet, X-rays, gamma rays. They all have wavelengths outside of this visible range. So when you think about it, visible light is really a very, very small part of electromagnetism. If you think about the range of frequencies, we're talking about on the order of 10 to the 25th, 1 times 10 to the 25th. And so we're talking about an incredibly small range of frequencies that we would call the visible light. And that light is just in the right place to enable photochemistry. It's energetic enough to enable most chemical reactions, to excite valence electrons, the higher orbitals, as required by photosynthesis. sometimes kids will ask me, they'll say, why is the grass green? Now that is a hard question to answer for a child. I mean, I could tell them that it's a quantum mechanical effect, that it absorbs some of the light from the red part of the spectrum and some from the blue part of the spectrum, and the green is left over. That's why grass is green, but that doesn't seem to go well with kids when you talk about quantum mechanics. Talk about higher frequencies, like UV and X-rays, gamma rays. They interact with atoms in a different way. Gamma rays interact with the nucleus of the atom, and the X-rays interact with the inner shell electrons, and the UV interact with the more of the outer shell electrons. But they can be energetic enough to completely strip the electrons from the atoms and will destroy biological molecules. And so you can't use that part of the electromagnetic spectrum as far as life is concerned.
This is one of the reasons that people have talked about why they're so dangerous. Gamma rays, and we know about X-rays. I mean, you go to the dentist and they still put the big heavy lead vest on you, and that's right. That's the reason right there, is because it has the potential to destroy those cells, as you're talking about, on the inner part of the cell, the atoms, I should say, and and therefore the cells that go along with it. So we have the perfect visible light for photosynthesis, as you were saying, and this has to be more than just a coincidence that we have this narrow band of visible light that comes to us from the sun. So that is remarkable.
Well, those gamma rays that are so harmful are blocked by the upper atmosphere and can be best observed from space. The visible light is observable. There's some atmospheric distortion. Most of the infrared spectrum is absorbed by the atmospheric gases, and again have to be observed from space, like we have with the James Webb Space Telescope, which is tuned to the infrared spectrum. We can see radio waves, but long wave radio waves are blocked. And so there's really a very narrow range of frequencies or energies that can actually make it through our atmosphere, so we can actually see the light that comes from the sun as well. I do a demonstration. I have 3 laser pointers, and they're all made the same way, have the same power, and I shine them up on the wall and ask the kids which one is the brightest. So I have a blue one, a red one, and a green one. And they all say the green one. And I say, okay, well, why is the green one brighter? It got the same batteries, got the same construction and so forth. And the reason why is because God has designed our eyes to actually see best in the green part of the spectrum.
Wow.
And then I say to the kids, I say, well, where does the sun put out most of its energy? Again, in the green part of the spectrum.
Wow.
It's almost like the same person who made our eyes made the sun.
Yeah.
That goes back to our previous discussion just a little bit about the chemistry of the sun. I remember it's a G2V, and I remember that it was, they sometimes refer to it as yellow dwarf, but it's basically the white light that comes to us from the sun is just the perfect light for us here on Earth.
That's right. That's exactly right. And so you can also see how the water molecule is made just right, because, I ask the kids, I say, well, how come water sometimes looks like it's colorless, like in a glass of water, and sometimes in deep bodies of water, it looks blue? And many times they give me the wrong answer. They tell me because it reflects the sky, but it doesn't. I tell them if they find that in their textbook, to tear that page out and throw it away. But what it does is water can actually absorb all the different colors, but blue, because of the size of the water molecule, actually reflects the blue back out again. But if you go down deep enough in the water, you'll thousands of feet down, then it'll absorb the blue as well, and it'll become black down there. And so if you think about it, you have this small band of radiation that can come through. If water was any different than it is now, it would block all the sunlight. Every time there was a rainstorm or a cloudy day or whatever, we wouldn't get any irradiation on the Earth at all. And so the water molecule and the light work together perfectly to give us what we need.
Now, for those of you who are listening, as you think about how practical Dr. Matzko is being here, he has his own website. It's George Matzko.
It's GeorgeMatzko.
Okay, .com. Am I remembering correctly?
That's
and
right,
it's
yes.
Matzko Science Ambassadors, and we encourage you to go and look on their website there. You were talking a little bit about this bombardment of really the solar wind, I think it's called. How does that interact, say, with the aurora borealis or northern lights? How is that recognizable, and what it does, and it's been in the news here lately, what it does to electronic equipment?
Okay, so the sun puts off a lot of energy, not all of it electromagnetism. There's actually particles. There's coronal mass discharges that come from the sun. For example, there was a big coronal mass discharge in 1859. It's called the Carrington event. And one of these blobs of solar material hit the Earth directly during that time. And back then, their technology was telegraph. So the telegraph keys went wild. They were chattering along. Some of the paper they used to record the Morse code caught on fire.
Oh, wow.
And they were able to see aurora, these beautiful colors in the sky, as far south as Havana, Cuba.
Wow.
During that time. We haven't seen anything like that since 1859, the Carrington event. If something like that happened today, we have a lot more electronics, and we think what would happen is it would destroy those big transformers that power our electric grid. And because we don't have that many spares, they only have like a month's worth of spares. Some estimates are that it would take 2 years to completely restore the power grid after being hit by one of those things.
That is a really fascinating discussion in and of itself right there. We're talking to Dr. George Matzko, and one of the reasons that we are talking with him is we have several solar eclipses that are coming up here very shortly. This is being recorded in 2024, but we're seeing that there are a number coming up, even all the way down in Australia, 2 of them, in fact, that are going to crisscross down in Australia in 2028 and 2030, if I remember correctly. We have really enjoyed talking to you on the broadcast today, and Dr. Matzko, thank you for joining us. We'll return again on the next broadcast to talk more about this.
Thank you. Enjoyed it.
Thank you again for joining us for these series of conversations with Dr. George Matzko. He can be reached at his website, georgematzko.com. That's GeorgeMatzko.com. The Matzko Science Ambassadors. These broadcasts are brought to you by LiveServeLead.com. Live, Serve, Lead, helping others succeed.